first off, good morning and good afternoon. Welcome to Lenaro Tech Day session on heterogeneous hardware accelerated OCI containers and secure OCI containers. I am Wes Skeffington, and my co-presenter is Stefano Stavellini. We both work within the systems engineering and systems software team at Xilinx. And what we're hoping to talk to you today about is briefly about a concept and collaboration opportunity that we're seeking around extending the OCI framework to bring heterogeneous hardware and VM isolated containers as first-class citizens into the OCI ecosystem. So in that light, the high-level goal that we're working towards, and the reason we're wanting to work with this community, Lenaro in general, and a broader set of software and silicon vendors, is to work with the OCI committee and extend the specifications to support the utilization as a framework for more heterogeneous hardware capabilities within the containers ecosystem. And so what do we mean by heterogeneous hardware? First, we're talking about things like accelerators that can be implemented in FPGAs, GPUs, et cetera, and not replacing them, but really tying them into the OCI for deployment and then container access to those accelerator resources. Second is we want to create this, call it a common dashboard or a common pane of glass for managing these heterogeneous platforms. And that includes things like the asymmetric multi-core processing that many of us implement in Cortex-R and Cortex-M coprocessors that sit next to your application processors. And then lastly, overall kernel deployment. We'll talk about this as a thing called RunX, where we're standing up containers as isolated using Xen hypervisor as a reference implementation. And of course, that can be extended to other hypervisors. So what's the overall motivation here? The real motivation here is that recognition that the OCI is quickly growing as an application packaging and deployment framework. And it's not just happening in data centers, it's also happening at edge targets, whether your edge is an on-premise server, or you're talking about the very edge where the digital physical boundary is bridged in microcontroller type devices. Simultaneously, our application performance growth is really ever more dependent on heterogeneous platform targets, whether those be things that we call domain-specific hardware architectures, et cetera. But we have really a big motivation as a broader compute industry and software industry to really bridge this gap between the container software ecosystem and these increasingly domain-specific hardware architectures. So that's really what we're trying to work towards. So first, we're going to talk about linking heterogeneous hardware accelerators and to native Run-C containers. And again, what we're trying to do is do this at a level within the OCI framework that is agnostic to the different orchestration frameworks and other technologies that people have built on top of containers in terms of container management and orchestration. So if we look at just a heterogeneous hardware access at startup, what we're specifically talking first to is an image spec extension to be able to have this additional metadata, key value pairs to identify that there's an incremental resource required for the container, and then where and what is that device data associated with that. So in this example, we've got an FPGA-based accelerator. We would represent that in the image manifest of the container with this device name and then pointing to the associated FPGA bit string that would be programmed. Container D would then know how to unwrap that and work with the device-specific configuration triggered based on that resource metadata hook. The device configuration block would then take care of the device-specific functionality to get that resource and bit stream loaded into the system, and then return that device name and any other associated information to the shim that can be used by runC to actually stand up the container and expose the associated hardware resources that that container is going to access. In terms of how we go do that, we are working, or we've looked at in our existing prototypes, just passing those as extra arguments when we call runC, but a more scalable solution might be in terms of the dynamic definition of the config.json file associated with that container. So again, it's not about replacing Kubernetes or runC or containerd in itself. It's about being able to use those mechanisms as an orchestration framework for tying into these heterogeneous platforms. So then if we flip that and look at the other side of it, because as you look at resource management, obviously there's startup and shutdown piece of it, kind of works in the opposite manner, where once we get the stop command for the associated container, we can shut down and stop that container and then bring back that state information to the device configuration. So in this case, or this example of an FPGA-based accelerator, then we can tear down and free up that partial reconfiguration region, say, within the FPGA or what other device that you're talking to. So that's sort of the example of using runC in combination with the heterogeneous accelerator orchestration framework. So with that, then we'll jump into talking about the concept around secure containers with the Zen. And it looks like Stefano, you're online.
Yeah, I'm in. So, all right, I can take it from here on runX. So let me add a few words on what runX is before we draw a parallel to what just Wes described in this world. So runX is a new OCI-compatible container runtime engine and is under LF-Edge. So the idea is that it can be used to run containers securely using Zen hypervisor technologies. So what it does is it creates a very small virtual machine, as small as possible, just enough to create an environment to run the container inside. So the benefit is that it's just a very different runtime environment from a normal container runtime like runC. So it has very different properties. For instance, as much stronger real-time separation and isolation and stronger security guarantees. Yeah, so it's a micro VM in the sense that the kernel and RAM disk provided by runX to run the container inside. And if you look at, there is a color scheme, darker blue is provided by runX, while lighter blue is the container itself. So is there going to be as small as possible, just a smallest possible environment to run the container? Wes, you can one slide. Right, but one of the first thing that we want to do, which I think is very interesting, is to extend the OCI image specification so that we can also describe kernels and RAM disks. So the idea is that a kernel today, container today, is basically a user space Linux or in general POSIX set of binaries, but it could be containing kernel space binaries too. So, for instance, you can imagine a container rootfs coming with a kernel binary inside. Under /boot or somewhere else, be flagged as a kernel. So there could be a key value pair in the manifest saying, look, this container actually also contains a kernel. And then runX will go look at this manifest, find the key value pair, and then it will actually use the kernel and RAM disk that come with the container to start the VM. So if you think of why will you want to do that, there is actually a very good use case for this. Next slide. Yeah, an RTOS. So you might wanna run an RTOS and deploying it dynamically using runX. So a real-time OS like Zephyr, you can imagine building your application using Zephyr or FreeRTOS, one of those, and because you have real-time or determinism RQ latency requirements, and you still want to deploy dynamically, right? You might still want to benefit from the lifecycle management the OCI tools come with, which is very powerful and very convenient to use. So what this allows you is to build your application as an RTOS, as a proper kernel RTOS, and then pushing it to the Docker Hub, and then dynamically deploying it using orchestration framework like Kubernetes, using Containerd, using all your regular OCI tools, and transparently your RTOS will get run inside the VM, and it will also show up as one of the containers running in your system. Next slide. And this now ties back exactly what Wes described in detail earlier, which is you can still do the same thing with accelerators and hardware assignment to containers that are run with RunX. Containers that are run with RunX, they could be both of the kind that come with the kernel or of the kind that the kernel is provided by RunX. But either way, this accelerator can be still configured correctly by the device configuration component, and then the hardware resources such as MMIO region, RQ, and anything related will be directly assigned to the VM so that the container can have direct access. And with that, I give you the ball back to you.
All right, thanks, Stefano. So again, sticking in this framework of the OCI really being valuable in terms of a management and deployment common pane of glass for a heterogeneous set of platforms. If we look at AMP, or asymmetric multi-core processing, there's an existing solution, at least on target for that, around OpenAMP. And it's a great framework that within Linux makes use of remote proc. And so we thought a logical extension of that, such that that same set of firmware resources could be managed through that common pane of glass for the overall system management, was to extend this same idea of a resource and device data, but tying that in now to, say, RPU or Cortex-M firmware that can be managed through that same device configuration block. So again, what this would look like is from it wouldn't be a traditional Linux container, but really it's just the packaging that goes around it to enable that to be deployed, and then with the on-target Containerd and Containerd shim, pass that information to the device configuration, which then can interact with remote proc and the corresponding slave processor. So again, it's not about replacing OpenAMP, it's about adding a layer on top of OpenAMP to be able to support those Cortex-R and Cortex-M firmwares in a common deployment infrastructure. So to talk to where are we looking for collaboration, why do we want to really engage with the broader audience here, is that really we've seen a lot of vendor-specific implementations around enabling containers and container orchestration for heterogeneous hardware, but they're just that, vendor-specific. And so we want to take a crack at really working with the Open Container Initiative Committee, such that we can get these changes associated with the image specification and the runtime specification upstreamed in a manner that provides a common design pattern for folks to tie their heterogeneous platforms into the OCI deployment infrastructure. So within the OCI image specification, three key things that we are working towards is really definition of the key value pairs for heterogeneous accelerators. So we talked about the resource, device data, kernel, RAM disk, as just initial examples of what the key value pairs that we're trying to work towards. Also talking about where does one locate the device-specific configuration data packaging within the container image. In our existing prototypes, we are just, we've picked a definition of this, but where we need feedback and collaborations, does that work for everybody? On the runtime specification in our prototyping efforts, we found that Containerd often does some filtering or removal of relevant image spec data that we really think is required for device configuration. And so making sure that we get a standard definition in terms of how Containerd treats some of these additional key value pairs that we want added in the image spec. We also need to standardize the way the container device configuration data is really passed between the container and the host. In our early prototypes, we were using some of the environmental variables passing. I think that's going to be a little bit brittle. And this is again, whereas we look to what's the right long-term solution so that we can do this in a standardized design pattern. And lastly is being able to standardize the method by which we export those dynamic hardware devices to the actual container itself. So these are sort of or 6 top-level things that we're really looking for collaboration within Linaro and other contributors to upstream within the OCI specifications. So just in summary, Xilinx right now really has a small development team that's working on prototyping this. Of course, we're doing that within the context of FPGA SoCs. And we really are looking for additional inputs so we don't have a overly vendor siloed view of what different platforms need from configuration data and the way that that needs to be passed. And then ultimately really looking for a multi-customer, multi-vendor drive to getting the OCI committee to support the specification changes that we're advocating for. As Stefano mentioned, we already have some collaborations underway with Project Eve within the Linux Foundation Edge organization. You can go to that wiki and kind of see where things are in terms of that progress around the RunX efforts. And really our key message here is this is an early proposal. We're working early prototypes within our team. And really what we're asking for is other contributors here that would see benefit or help here for managing these heterogeneous accelerators, asymmetric multi-core systems, et cetera. And again, the key value here is really about an integrated standards-based solution for the infrastructure that can be used in a way that is not vendor specific. So if you're interested in participating, giving some input and helping steer some of the early prototyping work that our team is doing, please reach out to myself and Stefano. And with that, I think we've wrapped up